All right, so we're going to talk about real numbers and some of their properties. These are properties that you all have seen and know, but you may not remember exactly what they're called and things like that. So if you need some, you can either take notes or as you're working the assignments, you can always open up the book, the e-text to the page where these are listed. And that way it'll help you through it. So we're going to look at subsets of real numbers and recognize properties of real numbers. Now, we've already talked about a couple of subsets of real numbers. We've talked about whole numbers and natural numbers. Have we talked about integers? I can't remember if we talked about integers. Did we? All right. So if you'll notice, basically real numbers. Now, everything we do in Bridge Math is going to deal with a real number. You may remember from Integrated 3 imaginary numbers that had the little I on it that come from the square root of a negative number. We're not going to deal with imaginary numbers. So all the numbers we look at can fit right here on this little chart, the real numbers. Real numbers are divided into two separate ones. They're irrational numbers, which we talked about, that have that decimal that goes on forever and ever and ever and never ends, or rational numbers. All rational numbers can be written as a fraction. The decimal either repeats or terminates. And within the rational numbers, all our integers fall. Integers are all positive and negative numbers. They're all considered rational because you could write them as a fraction, right? Any number can be written as a fraction if you put it over 1. Whole numbers are the numbers 0, 1, 2, 3, and up, and then the natural numbers are 1, 2, 3, so on and so forth. So that are really all the subsets of numbers we talk about. So remember, natural numbers are the ones you count with 1, 2, 3, 4, 5, and it goes up forever. Whole numbers are all those natural numbers, including 0. So it goes 0, 1, 2, 3. Then when we talk about integers, we bring in all our negative numbers. And then the rational numbers are any number that has a fraction, a decimal that ends, a decimal that repeats. So if it doesn't fit in with integers, whole numbers are natural numbers, but it can be written as a fraction. It is just listed as a rational number. So what they want you to do is basically take like these groups of numbers. So we're just going to look at -7 right here first. And it wants you to list the sets of numbers that it belongs to. And first of all of these are going to be real numbers. So I can list F with all of these, right? Okay. Now, from there, -7, or also rational numbers and irrational, it can't be both D and E, right? Irrational numbers are sort of separate from everything else. So if we get to an irrational number, that's the only thing it's going to be outside of a real number. Now, the other numbers could be all 4 of these. It could be 1, could be 2, 3, or 4 of them. And as we look at it, -7, we already said -7 is a real number. It can be written as a fraction as -7/1, so that means it is rational, so it would be a D. I would list it as a D. Then integers are the numbers that are positive and negative without any decimal or fraction parts, so -7 fits that, so it would be an integer. However, it is not a whole number. Remember, whole numbers are 0, 1, 2, 3 all the way up, and natural numbers are 1, 2, 3. So if you're working backwards, once you get to one that it's not going to be anything less than that out of these last 4 right here. So -7 is real, it's a rational number, and it is also an integer. Now, -3/4. Once again, F is going to go with all of these. I'm going to put below for square root of 5, pi, 7.3, square root of 81. These are all real numbers. All right. Now, irrational or rational, can it be written as a fraction? Well, obviously, it is a fraction. So negative 3/4 is a rational number, but that's going to be it. It is not an integer. Integers, whole numbers, and natural numbers, all of those don't have any fraction part or decimal part. It's just a number. If it's an integer, it would include negatives. If it's whole, it would include 0. Natural, it would just be the positive numbers. So negative 3/4 is only a rational number. It doesn't fit any of those three. The number 0, once again, 0 can be written as a fraction as 0 over 1, so it's rational. It is an integer. Integer includes 0 and positive and negatives. And so I'm going to put C there. And it is also a whole number. The whole number set includes 0, 1, 2, 3. However, it is not a natural number because natural numbers are only 1 and up. All right. And then 0.6 repeating, it's irrational or rational? Irrational is if the decimal goes on forever without repeating. That repeats. So that means it is a rational number. And that's going to be it. Integers, whole numbers, and natural numbers don't have any decimal parts. Square root of 5. 5 is not a perfect square, so that's what we talked about last class period. A square root of a number that's not a perfect square is going to have one of those decimals that go on forever, which means it is an irrational number. And if it is irrational, it can't be any of the other four, so I can stop right there. Pi, remember pi is one of those that goes on forever. It's just like the square root of a number, so pi is real. And it is an irrational number, and that's it. 7.3, it is rational because its decimal does terminate. So since it does terminate, that does make it rational. But that's going to be it. It's not going to be an integer, whole, or natural because it does have a decimal part. And then the last one, they're trying to trick you. The square root of 81, it is rational because the square root of 81 is 9. It is a perfect square. So we're actually looking at not the square root of 81, but just the number 9, which is a rational number because it can be written as a fraction. It's an integer because it doesn't have any decimal or fraction part. It's a whole number. And it is a natural number too. All right, so some of your assignments, you're going to be asked to list, label numbers into what specific sets of numbers it is a part of. All right. Properties. All right. So there's several properties here we're going to go through. And this is where you might want to pull up or you might want to take a picture of this where you have it, or you can pull it up on your e-text. At home, you might want to take a picture of it. That way you're using it. You have it there as you're working through, or you can pull up the e-text. This is in the e-text for chapter 3.5. All right, the closure property of addition. All that means is if you add two real numbers, your answer has to be a real number. So if you add two numbers that are real, you don't all of a sudden get an imaginary number. If you add a real number to a real number, your answer has to be real. Same thing with multiplication. If you multiply two numbers that are real, the answer is going to be real. You can't get an imaginary number out of multiplying together two real numbers. All right, now here's the ones you're going to use more of. Commutative property of addition and commutative property of multiplication. All that says is it does not matter what order you multiply or add two numbers. 3 plus 4 is the same thing as 4 plus 3. It doesn't matter which order. Same thing with multiplication. 2 times 3 is the same thing as 3 times 2. And so over there it shows you 13 plus 7 is equal to 7 plus 13. If you use square roots, it's the same. 13 times 7 is the same as 7 times 13. So the commutative property just states for addition and multiplication, it doesn't matter which order the two numbers are in. Okay, that's the commutative property of addition or multiplication. Obviously, if it's a plus, it's addition. If they're pushed together or a multiplication symbol, it's property of multiplication. All right, so if you want, I see. All right, gotcha. Our next property, the associative property of addition and multiplication, means if I'm adding 3 or more together or multiplying 3 or more together, it doesn't matter which two I add together or which two I multiply together first. Okay? So if you notice right over here, right here, if I've got 7 plus 2 plus 5, and I add together 7 and 2 first, then I add together 5, that's going to be 9 plus 5, which is 14. The associative property says it's okay for me to add 2 and 5 together first to get 7, and then add it to 7, it still equals 14. All right? So it really doesn't matter how you group them together, if they're all addition or if they're all multiplication. That's the associative property. If you notice the same thing below, 7 times 2 grouped together times 5 is the same times 7 times 2 times 5 grouped together. All right? The next one is the distributive property. And most of the time you just call it the distributive property. I guess the official is distributive property of multiplication over addition, but generally we just say the distributive property. Basically that means is if we have a number multiplied by an addition or subtraction problem in parentheses, you get the same thing by distributing, right? If you multiply the number on the outside of the parentheses by everything on the inside of the parentheses, and now we can rewrite it without parentheses, that is the distributive property. If I had 3, the way we see it most often is 3 times x plus 3, right, with an algebra term or a variable. We would multiply that 3 by both of those, and that would become 3 times x is 3x. 3 times 3 is 9. That would become 3x plus 9. Okay, so that's the distributive property. All right. Identity property of addition. Okay, the way I remember that is what can I add to something to get identically what I had before? Well, it's 0. The identity property of addition means if you add 0 to something, you get what you started with. Okay. Square root of 3 plus 0 is square root of 3. 0 plus pi is pi. 100 plus 0 is 100. We all know that. That's called the identity property of addition. All right. Likewise, there's going to be an identity property of multiplication, but it's different because what do you multiply something by to get identically what you just had? 1. Anything times 1 gives you what you started with. So that's the difference between addition property of identity addition and identity property of multiplication. Identity of addition, you're adding 0 to get what you started with. Identity property of multiplication, you're multiplying by 1 to get what you started with. Okay. The inverse property of addition, the inverse property basically says what adds together to give you 0. What are opposites? Adding opposites. Well, if you add a number and it's negative, it's always going to equal 0. That's the inverse property of addition. Okay. Negative square root of 3 plus the negative square root of 3 is 0. Negative pi plus pi is 0. 1,000 plus negative 1,000 is 0. Inverse property is adding opposites to equal 0. All right. What is the inverse property of multiplication? Well, it is what can we multiply together to get 1. And you multiply by its inverse. That's why I can remember the inverse property. Right? If you have an inverse, a fraction, if you have 3 over 4, what is its inverse? Its inverse would be if you flip the fraction over. And anytime you multiply together inverses, that would be 12 over 12 which is 1. All right. Remember, if a number like 3, what's the inverse of 3? Well, we would have to write 3 as a fraction, which would be 3 over 1. And so its inverse would be 1/3. So if it's not in fraction form, put it over 1 and then flip it over, and that's the inverse. And then multiply those two together, always equals 1, is that inverse property of multiplication. Do we have any more? Okay, so we want to name the property illustrated. All right. Square root of 3 times 7 equals 7 times square root of 3. Notice we just moved it around. We put them in different orders. It's multiply, so that is the commutative property of multiplication. And I'm just going to put an X for multiplication. All right, notice the next one. 4 plus 7 plus 6, 4 plus 7 plus 6. It's all the same order. The only difference is we are grouping them separately. Grouping them different. Remember, that is the associative property of addition because it's adding. All right, C. We have a number. That's the telltale sign for this. The number on the outside of the parentheses, and then we don't have parentheses. That is the distributive property. All right. Now this one, they're trying to trick you because of the parentheses. If you look at it quickly, it looks like it is the associative because I'm grouping them different. But notice in both sides, square root of 3 and square root of 7 are grouped together. So I haven't changed my grouping. All I did was change the order in which I added square root of 3 and square root of 7. So that is actually commutative. Doesn't matter what order. The commutative of addition. All right, so that's what there'll be a lot of that in here. All right, here's a couple more. All right, 17 plus negative 17 equals 0. All right, there's 2 there. There's the identity. The way I remember the identity is, do I get identically what I started with? No. So this is actually the inverse. This is the inverse of addition. The inverse of addition says if you add opposites, it equals 0. All right. So you may see why it will be good to have pictures of this or be able to pull up your e-text and have that page sort of sitting there that you can look at. Now this one, square root of 2 times 1 equals square root of 2. I started with square root of 2 and I ended with square root of 2. I get identically what I started with. That is the identity property of multiplication. All right. And I believe that's it. All right. So